All right, welcome back, everybody. We are starting chapter 6, which involves uniform circular motion and gravitation. So we're just going to talk about uniform circular motion today. We're going to get a definition, and we'll get a couple equations and a couple scenarios to look at where uniform circular motion takes place. We'll also connect uniform circular motion to forces in Newton's laws. They're very much connected, and you'll see a lot of crossover between the two, which is kind of nice. Also, a few new things, but overall, it's very similar to the forces unit that we just looked at. So let's talk about what uniform circular motion actually is. So you will see this referenced as UCM. And so this is just motion in a circle at a constant speed. All right, so notice how I say constant speed, and that was very intentional. Remember that speed is how fast something is going. The direction that it's going doesn't matter. We would not be able to say something is moving in a circular path at a constant velocity. That is impossible because of the definition of velocity. Velocity changes by definition if the direction is changing. And if something is moving in a circular path, it is changing direction at all times. So if we have a circular path here, if we were to draw the velocity vector at any point, all right, so if we draw the velocity vector, so the object is moving this way around the circle, the velocity vector at this moment in time, this instant, would be a straight line that would shoot tangent to the circle. So that would be the velocity vector. And then if we drew a velocity vector at this moment in time, it would be straight line tangent to the circle in that direction, and so on. And so we could do that at any point, and we know that the velocity at that moment in time is pointed in that straight path direction. And of course, at the next instant, it is now pointed in a different direction. But if the speed is constant, then the magnitude of the vectors is the same, so the length, we would say, is exactly the same. So if you're driving around a curve at 35 miles an hour, assuming it's a circular curve, your speed could remain constant. Maybe you have cruise control on or something like that, but your direction is constantly changing as you go around that curve. So that would be considered uniform circular motion. And so all these calculations, all the equations we're going to look at will deal with uniform circular motion. And same with the idea of gravitation and orbits and things like that. We are going to assume, for simplicity's sake, because it's not always the case in real life, that objects stay at the same speed when they're moving in a circle or orbiting. But we can make some generalities, some general assumptions that make our life a little bit easier for the calculation aspect of this. Okay, so velocity and acceleration in a uniform circular motion. All right, so I'm going to move this kind of down here so you can see everything. So speed of a particle in uniform circular motion is constant, but the velocity is not. This is exactly what we just talked about. And so if you look at this example here, or this picture here, the instantaneous velocity, just like we talked about on the previous slide, is tangent to the circle, right? So we look at that right there, tangent to the circle. So there's the velocity. Now, the acceleration is pointed towards the center of the circle. Now, this might be something that's a little hard to wrap your head around, but this is always the case in uniform circular motion. The acceleration is pointed towards the center of the circle. All right, instantaneous acceleration at any point, always pointed towards the center of the circle. So make sure you write that down. Make sure you start drilling that into your head because it's very, very important. acceleration pointed to the center of the circle. Now, we'll get into some details when we relate this to forces about what that means, and hopefully you have some idea about, if you know the direction of this acceleration, you may know something else, the direction of something else which is related to forces. We will talk about that a little bit later. So this is called centripetal acceleration. It's our first equation. We have the acceleration of an object moving in a circular path at a constant speed is equal to the velocity, the linear velocity, squared, divided by the radius. All right, pretty straightforward. All right, I'm not going to go into the derivation of this, but this is our equation for centripetal acceleration. The word centripetal just means center seeking. All right, center seeking. So that kind of gives us, it should make some sense that the acceleration is pointed towards the center. All right, so a classic example, and if you were in class with me, then you'd see that I use this example all the time, a ball on a string. It's very simple and very good visual demo. So the ball on the end of a string is being swung in a horizontal circle, so that's a flat circle. The ball is accelerating because, all right, so we already discussed this, but the speed is changing, the direction is changing, speed and the direction are changing, the ball is not accelerating. Anything moving in a circular path is accelerating, so D is out. Speed, we said, is by the definition of uniform circular motion, the speed is not changing, it'll be staying the same, and the speed and the direction, we already said the speed, so B, of course, is the answer, the direction is changing. Okay. All right, so same idea here. We have a car turning a tight corner at a constant speed, top view of the motion here. So the car is going at this moment directly to the right, but of course it's going to change. The velocity vector points to the east. What direction is the acceleration? Perpendicular to the velocity at any instant. That's another way we could say it, that the acceleration vector is perpendicular to the velocity. So it would go straight down this this dotted line. So that would be your acceleration vector, pointed right down that way. All right. What we're going to talk about in a little bit is what causes something to move in a circular path. All right, now think about this, because what we've talked about when we talk about Newton's laws is what causes something to accelerate. All right, and anything moving in a circular path is accelerating. So there is maybe a little hint to the connection between Newton's laws and circular motion. Ball at the end of a string is being swung horizontal circle. What is the direction of the acceleration of the ball? Tangent to the circle, in the direction of the ball's motion, or towards the center? All right, again, we're talking about acceleration. These are all questions asking the same thing. Now, so that should kind of clue you in here. This is important, all right? Here's the center of the circle, here's the string, here's the ball, and it's moving around that way, let's say, all right? Well, the acceleration, as we said, is pointed towards the center. So there's the acceleration, and the velocity at that point would be moved that way. So B is the answer. And so in this case, with a ball and a string, what is keeping the ball moving in a circular path? This is always the question we're going to want to ask. What is keeping the object moving in a circular path, no matter what the scenario is? And so in this case, of course, it is the string. Right? The string is keeping the ball moving in a circular path. The ball, what does it want to do? Well, because of its inertia, the ball wants to move in a straight line. It wants to move in the direction of the velocity at any given instant. But what happens? The string says, nope, you're not going straight. You're going this way on this circular path, and I'm going to make you do it. All right? The string causes the acceleration that is always pointed towards the center of the circle. All right? And think about it, the string is supplying a force. Okay, that's important. All right, when we talk about circular motion in general, we talk about frequency, period, and speed. All right, so we'll talk about period and frequency first. So period, and you may have come across these terms before, is the amount of time it takes for one revolution. All right, so how long does it take to go around once? That is considered the period of the motion of this object. All right, so we talk about periods of time, right? Like there's different, but it is a time. It's usually measured in seconds, but if we're talking about the orbit of planets and satellites and things, it could be hours, it could be days, it could be years, it could be decades, right? Depending on how long it takes. Now, of course, orbits are not perfect circles, but they are pretty close to circles, so we can estimate that and get a really, really good estimation on that. So the amount of time it takes for one revolution or repetition of some event, okay? It's measured in seconds. So you could say seconds per revolution or just seconds. Most of the time we will be using seconds as our time, but like I said, it will change from time to time, different scenarios. Frequency is just the inverse of the period. So it is number of revolutions per second. All right, so it is the absolute inverse. So if you know the period, if you take 1 divided by the period, you will get the frequency. If you know the frequency, you take 1 divided by the frequency, and that will equal the period. So period, also I want to say, period is represented by capital T, and it is 1 divided by the frequency, right? Measured in seconds. Okay. Number of revolutions per second. So sometimes you will see this as a unit of revolutions per second, or seconds to the -1, or maybe seconds to the -1, like that. All right, the inverse of seconds. So either one can work. So that's written right there. And frequency down here equals 1 divided by the period. Okay. If you look on your equation sheet, let's see, we have the period equals, let's see if I can hold that. Right there. There we go. That equation. The period equals 1 over the frequency. 2 pi over omega, that is a rotational quantity. We don't know what that means yet, so don't pretend to use those variables. That's not going to help. But period being 1 over the frequency, that is the key here. Okay. All right, let's take a look at this. We're going to talk about speed here. And so if we're talking about speed, moving in a circular path, velocity in general, all right? If we want to just an equation for velocity, velocity is equal to distance or displacement divided by time. If we think about the distance that something travels when it moves in a circle, well, that's just some geometry, right? So you can say 2 pi r, that's the distance that it travels, divided by time, or the period, how long it takes to go around once, all right? And so the velocity can be measured. That can be in meters per second, or it could be centimeters per second, or maybe light years per day, or something like that, all right? But it's a unit of speed. That can also be written as 2 pi r times the frequency. which is shown right here.